Okay, good morning, everyone.
Good morning, sir.
Thanks.
Okay, so today we're gonna be taking a look at sound waves, right? Sound waves, which what are we going to be looking at? We're going to be looking at the production, the propagation, what makes a song loud, what makes the pitch high, and so on, right? And we're going to classify the frequency of sounds. Hopefully, we get all of that done today, and maybe in the next video we will take a look at the uses of ultrasongs and all of those things, like uses of sound waves. So, does anyone know, or do anyone know, I should say, um, how sound waves are produced? So, production of sound waves.
through through vibration.
Mechanical vibration.
Right. So, they are produced by mechanical vibrations, right? So, you could say sound waves, or these are produced via mechanical vibrations. Right. So, if something is vibrating, any mechanical object is vibrating, or once you have a mechanical wave, you basically have a sound wave. You may not be able to hear it, but there is sound waves there. Right. So what about the propagation of sound waves?
They happen through state of matter like solid, a liquid, or glass, and they go through waves like that.
Okay. It's a propagation of sound waves. So they could only travel through material media. Right. Remember that sound waves are longitudinal waves, which means that they could only travel through mediums. What are the other kind of waves that could travel through maybe a vacuum? What are the other type of waves? Uh-huh.
Lights.
Yeah, well, what kind of wave is a light wave?
Progressive waves.
What?
Transfers.
Yes, it is a transverse wave, right? So it is a transverse wave. So how the propagation of energy or the sound wave takes place in the material, right? So each particle passes on the vibration to the one next to it or to the adjacent one. All right, so I wouldn't write that down, but that is an important note that the particles actually gives off the energy or passes the vibration onto other particles. Okay, and that is how the wave propagates through the medium. And the important note here is sound cannot pass through. Cannot pass through or propagate through. That would be the better. Will propagate through a vacuum. Right. So anybody would be able to tell me what is the what sound the Big Bang made, if it had one?
Well, we wouldn't know because there's a vacuum.
We would know because it was a vacuum. In fact, we would be able to hear it, right? Because the space is a vacuum. Very good. Nice. All right. So we would talk later about some experiments to test if we could hear sound in a vacuum or not. But for now, we want to move on to pitch and loudness. All right. So pitch and loudness. And when we talk about the loudness, we talk about volume, right? So that is, we can use that as that word as well. Cool. So what determines the pitch of a sound wave?
The frequency
Right. So the higher the frequency, the higher the pitch.
pitch.
Right. So, and what is the pitch exactly? What do I mean by pitch?
Well, basically like the tone of the sound, if it's a high pitch or a low pitch.
The tone. All right, I'll take that. Right. So a greater frequency. So we could say a greater frequency wave produces a sound of higher pitch, right? So produces a sound of higher pitch. Lovely. Right. So if we were to compare some waves, let's compare some waves. So the first wave I want to compare, remember we deal with wave fronts, right? So for now, so suppose we had something like this. Right, where we could actually see the rare refraction and the compression. Right, so we had like something like this. Let's write B, and C we had something like this. Right, so look at A and B. A and B has essentially the same wavelength because the distance between the compressions are the same. If you look at it like that. I remember the a wavelength is from crest to crest or trough to trough, right? Or in this case, compression to compression. Okay, so A and B can have the same wavelength, but notice that C has a different wavelength. Now, the speed of the wave, remember this is sound wave we're dealing with, so we can say that the speed here is the same because they are in the same medium. Right, so if they have the same wavelength by this thing, so F is equal to V over lambda. I remember that V is equal to F lambda, so we can solve for V. Okay, sorry, solve for F. If they have the same velocity and the same wavelength, that will mean that they have the same frequency. Right, so A and B has the same frequency. However, A's wavelength is shorter than C because this is a wavelength for C, this entire thing, and this right here is the wavelength for A. Right, so that would imply if the wavelength is longer, what would happen to the velocity is the same, so what would happen to the frequency of C? What would happen to the frequency if the wavelength is longer? So if this is a big number in the bottom here, frequency would be what? All right, let me make it a little simpler. Since V is constant, right? Since V is the same, we could say that frequency is inversely proportional to the wavelength. So what happens as the wavelength increases? Anybody can remember what inversely proportional means?
No, sir.
Okay. All right. So inversely proportional means as something rises, the other one decrease. Right? And it could try it. You could try it in a calculator. You could try like 1/2, 1/5, and you'll realize as you get the number in the denominator again larger, you will get it. You'll get the overall number being smaller. So as wavelength increase, frequency decrease. Right? Since it is inversely proportional. Now, since C has a lower frequency than A, what would that mean for the pitch? C would have a lower pitch because the frequency is lower. Right? So A and B has the same pitch, but C would be lower. Very good. I remember I cannot see the chat, so you'll have to talk. All right, and you could check frequency using a tuning fork. Right, using tuning forks and whatnot. What about the volume? What determines the loudness? What determines the loudness?
The displacements.
The displacement, which we call the what?
The amplitude.
The amplitude, right? So we could say that, we could say that the amplitude of the wave, or the greater the amplitude, the louder the sound, right? Now notice that the loudness or the volume doesn't necessarily have to do with the frequency, speed, or wavelength. Right? All it has to do is all it does is with the wavelength. All of that matters is the amplitude. Right? Now when you increase the volume on your radio or whatever it is, what do you think you're doing? You are actually increasing the amplitude of the sound wave, making it louder. Right? So I just wanted you to think about that. Right? And well, we could see a graph of this thing. Like we could determine pitch and loudness from a displacement time graph. So if we were to draw a displacement time graph like this, right? So this is time. Well, don't necessarily need to put units now, and this is displacement. Right. So suppose we have a graph like this. Right, so and they label the points, this point here A, this point here B. No, sorry. This point here B, this point here C, and this point here D. And we want to classify these things. So we want to get volume, pitch. We want to classify if the volume is high, if the pitch is high, if the volume is low, if the pitch is low. Right, so A would be what? The volume would be high because it is at maximum. Right, so we can see that the volume is at high, but the pitch is low because the frequency of the wave at that point is low. Right, in comparison, remember the frequency is the amount of waves passing per second. Right, here it has less waves than over here and here. Right, okay, so at B, the volume is low because it is at the bottom. Right, it is at a negative displacement. So the volume would be low, but the pitch would be high because it is many waves passing here per second. Right, at C, right, they say that, well, C was like somewhere up here. Right, C, the volume would be high and the pitch would also be high because the volume, it is at maximum, and the frequency is also very large because it's many waves passing per second. Right, and finally for D, it is at a lower amplitude than A, so it will be low, and the frequency will also be, well, the pitch will also be low because it is less waves passing per second. Right, and on the last part of today's class, the last place that I wanted to get at is the classification of frequencies of sound. Classification of frequencies of sound. Okay, so frequency below 20 hertz. So frequency below 20 hertz is called infrared sound, right? Infrasound. Right? I don't know where I got the infrared from because infrared is light, right? Frequency between 20 hertz and 20,000 hertz is what we call audible. That means we could hear it, and well, audible with respect to to humans, right? Right, it's audible, and of course, as they get older, it becomes difficult to hear higher pitches, so it will reduce to about 16,000, right, as they get older. Frequency above 20 hertz above 20,000 hertz is what we call ultrasound. And has anybody ever heard about ultrasound before?
Yes.
Yeah. Right. So what we just use ultrasounds for, and that is what we would see in the other video. Well, in the next class. Thanks for coming, and that's where we will close off class today. Any questions on this?
No, sir. No, sir.
Okay, no problem.